Hello and welcome to this video where I'll show you how to solve an ODE that is equal to a sine or a cosine function, but in a much more efficient manner than you've probably seen before. So if you could remember back to the undetermined coefficients method, you would say that the particular solution to this ODE is in the form a cosine of 2x plus b sine of 2x. But this usually took a lot of algebra. You had two unknown coefficients a and b, and sometimes it was even just a nightmare to solve for those constants, right? But actually, we can solve this ODE in a much easier way than guessing a cosine of 2x plus b sine of 2x. And the only sort of, supplemental knowledge that you need to know is Euler's relation. So e to the I theta, where I is the imaginary number, the square root of -1, equals cosine of theta plus I sine of theta. So this relation right here is going to actually allow us to transfer any ODE that's equal to sine or cosine into an ODE that's equal to an exponential. And if you remember, doing undetermined coefficients when the right-hand side is a exponential is just so much easier than if it's a sine or a cosine. Okay, and this is really all the information that you need to know that maybe you haven't seen before in your ODE class. So let's go ahead and get into the actual method here, okay? So first things first, we do still solve for the homogeneous part of this equation, and that's when the right-hand side is equal to 0. So nothing changes here. We write the characteristic equation out. R squared plus 4r plus 4 equals 0. If we were to factor this would give us a r plus 2, which is a double root situation. So we have one root, and that's -2. This gives us the homogeneous solution of c1e to the -2x plus c2xe to the -2x. Okay, so now is when we would typically guess the a cosine of 2x plus b sine of 2x, but instead we're going to do something a little bit different. We're going to create sort of a mother equation to the one that we are asked to solve, except this is a equation of complex numbers. And so let me show you what this looks like. We're given y double prime plus 4y prime plus 4y equals 3 cosine of 2x. But if we were to make this a complex equation with a new variable z, this is the same thing as saying z double prime plus 4z prime plus 4 times z equals, and then remember this is now a complex equation, and the reason it's complex is because we want to rewrite that cosine in terms of a complex exponential with Euler's relation. So let me write it one more time here just so we don't forget. So, well, we can write a 3e to the 2ix right here instead of a 3 cosine of 2x, right? And that's because if we were to expand out this exponential using Euler's relation, we would have 3 multiplied by a cosine of 2x plus a I sine of 2x. And so you may be wondering, okay, what happens to that I sine of 2x? And that's a very good question. We're actually going to make an important distinction here, and that's going to be that y particular equals the real part of z particular. And so that'll eliminate the I times sine, because if we want to take the real part of z, then we're going to forget about everything that's multiplied by I, and in that case, the sine is being multiplied by I. So if you wanted the real part of this equation right here, it would be this equation up above. And so that's kind of what saves us there. And so the most important relation here is that the particular solution of our nice y equation is equal to the real part of the particular solution of our z equation here. So z is going to give us a final answer in terms of a complex number. We just take the real part of it, and that's our nice answer. Okay, but that's a lot of talk, so let's get into what this actual method looks like, and I think you'll see very quickly that it's much easier than you've probably seen before. Okay, so we have this new ODE that we've created to solve, and so we need to guess the particular solution here. And if you remember, if it's an exponential, it's always just going to be an ae to the whatever was already in the exponent. So 2ix in this case. Then we want to take a couple of derivatives so we can inevitably plug it back into our z equation. First derivative, well, we can do the power rule here. Even though I is an imaginary number, it still acts like a regular number when you do calculus. So if we do a derivative here, this 2i is just going to come to the bottom because the derivative of 2ix is just 2i. So we're going to be left with a 2ai e to the 2ix, like so. Second derivative now. This is going to be a same deal, right? We're going to bring down that 2i. That's going to give us a negative 4a e to the 2ix. And where did that negative come from? Well, that's because I times I equals negative 1. Just a little bit of imaginary number information there for you, because I don't want to assume any prior knowledge of this subject. Okay. Anyway, though, we have everything that we need to plug this into the complex ODE up above, right? So let's go ahead and do that. We have a negative 4ae to the 2ix plus 4 of our first derivative. So this is going to be a 8ai e to the 2ix. Then we get to add a 4ae to the 2ix, and that's going to be equal to a 3e to the 2ix. Okay, let's cancel out 1e to the 2ix of every term. And then if you notice, we have a negative 4a plus a 4a. So actually these whole terms cancel, and we're left with a nice relation, 8ai equals 3. Okay, what does that mean? It means that a equals 3 over 8i. Now, an important thing to note here is because we want to take the real part of this particular solution, we need it to be in a easily identifiable form. That is, I need you to be able to look at that form and be able to tell me what the imaginary part is. And if I is in the denominator, you can't do that because every complex number is in the form a plus bi, right? And so it's really easy to tell me what the real part of z is. It's just a. But what if it was a over I plus b? Well, then it's not so simple, right? You could say it's b, but then what does a over I really mean? And so it gets a little bit confusing. All of that to say, we need to somehow write this I in the numerator. And there's a really nice relation for this. This is just something to remember, 1 over I, and something you can prove if you take complex analysis. 1 over I is magically the same thing as negative I, which I've always thought is pretty cool. So actually, a equals negative 3i over 8. Okay, so we found our undetermined coefficient, and I guarantee you it was about 5 times as fast as if we just settled with guessing a sine and a cosine. What do we say the particular solution here was? Well, we said that it was going to be a e to the 2ix. We now know what a is. It's going to be a nice negative 3i over 8 times a e to the 2ix. And remember, this is our z particular solution, and what we're actually looking for is the real part of this equation. The only way to know what the real part is to get this somehow into an a plus bi form. And here's where Euler's relation comes in. E to the I theta equals cosine of theta plus I sine theta, where cosine of theta is the real part and sine of theta is the imaginary part. So with that knowledge, we can easily write this in a plus bi form. We have a negative 3i over 8. With Euler's relation, we have a cosine of 2x, because whatever is not an I in that exponent, you write inside of the sine and cosine. Then we have a plus I times sine of 2x. Okay, now we can go ahead and distribute out this negative 3i over 8. And so what does this actually look like? Well, we have a negative 3i over 8 times cosine of 2x. And then we have a negative I times I, but remember I times I itself is negative 1. So we have a negative 1 times a negative 1. And so that's going to give us a nice plus. And then we have 3/8 times sine of 2x. And what was our goal with writing this new equation z? Well, our goal was still to find y. And we said that y was equal to the real part of z. And that's because y is equal to a cosine, which is the real part of Euler's relation. So what does that mean y is then? Well, there's an I on this term, right, because of this I right here, but there's no I here. So our real part of z is just a nice 3/8 sine of 2x. And this is the exact same particular solution you would get with the cosine and sine method, but this is much, much easier. So we can just write our final answer, which is going to be a summation of the homogeneous part of the equation plus the particular part of the equation. their respective solutions. We said this was a c1 e to the negative 2x plus c2 x e to the negative 2x for that homogeneous part. And now we have the particular solution, which is a 3/8 sine of 2x. And this is our final solution here. And so by kind of dancing around y, right, we were able to find a different equation's final solution and then piece together what y was based off of that, which in turn gave us the answer much, much quicker than if we had used traditional undetermined coefficients methods. Okay, let's go ahead and get into another example where it is actually equal to a sine, so therefore our y is then going to equal the imaginary part of the equation. Here we are with another ODE, except this time it's equal to a sine function, and so therefore when we cook up a new complex valued function, we're going to be looking for the imaginary part of it to satisfy our y particular solution. First things first though, we always solve for that nice homogeneous part of the equation, where g of x, or the right-hand side of the equation, is 0. To do that, we write this characteristic equation, r squared plus 2r plus 2 equals 0. Now we can go ahead and solve for r here, and unfortunately this is not factorable, but the quadratic formula is not so bad in this case. R equals negative 2 plus or minus, let's see, 2 squared, so just 4, and then minus a 4 times a 1 times 2. This is over 2 times 1, so just 2. R equals negative 2 plus or minus, what's 4 minus 8? That's going to be a negative 4, so what's the square root of negative 4? That's going to be a 2i, so this is plus or minus 2i over 2. Therefore, r equals negative 1 plus or minus I. What does that tell us about the homogeneous part of this solution? Well, this is going to be what we call alpha, and then we're going to imagine a 1 being multiplied by this I right here, and that's what we call beta. This gives us a homogeneous solution of e to the alpha x, so negative x, times c1 cosine of beta x, so just ax, plus the same thing but for sine. Okay, we have the homogeneous part of this equation down, so now it's time to get into the actual new equation that we're going to cook up. So we're going to keep the coefficients in front of the original ODE, except now we're going to rename y to z, and then we're going to set it equal to a complex exponential. So if you remember, our equation was y double prime plus 2y prime plus 2y, so I'm going to replace all of those with z's to start. And then what does this equal? Well, the original equation is equal to a 8 sine of 3x, but we want to turn that into an exponential, so we can do that with Euler's relation. And we can write sine of 3x as the imaginary part of e to the I times 3x. So let's go ahead and write a nice 8 to maintain the coefficient, and then an e to the 3ix like so. First distinction to make here is that what we're really looking for, the particular solution of y, is going to, in this case, be the imaginary solution of z. And why is that? Well, that's because y is equal to a sine now instead of a cosine. And e to the I theta equals cosine of theta plus I sine of theta. So actually this y is the imaginary part of this z instead of the real part like we had in the previous question. Okay, so with this distinction in mind, we can go ahead and guess for the particular solution of z, which is just a e to the 3ix. Nothing new there. And we can go ahead and take the first couple of derivatives to plug it back into the original ODE. This will give us a nice 3ai e to the 3ix. Second derivative is going to give us a negative 9a e to the 3ix. And that's just because when you take the derivative of an exponential, you take the derivative of that exponent and multiply it by the whole derivative. Okay, and so the reason we got this negative here was because we had an I from right here times another I from right here. Okay, now we have our first and second derivative, so we can plug this back into the original ODE. Okay, so I'll keep it up top. Let's have a negative 9a e to the 3ix. And then we had a plus 2z prime, so this is a 6a I e to the 3ix. Now we have a 2 times our original guess, so 2a e to the 3ix. Nothing changes about that right-hand side, 8e to the 3ix. Okay, first things first, let's cancel a exponential from every term. What do we see here? I see a negative 9a plus a 2a. So this is a negative 7a. And then I see a plus 6ai. And I see that's equal to 8. And so the goal here is to solve for a. So let's factor out an a. This gives us a negative 7 plus 6i, which is equal to 8. And so what does that tell us about a? That a is then 8 over negative 7 plus 6i. Okay, now this is going to be the coefficient a, but remember the point of this is to find the imaginary part of the particular solution for z. And so this is the coefficient in front of the e to the 3ix that's going to be in our particular solution for z. It's not so easy to tell what the imaginary part of this guy is. So we need to rewrite it in a form where we can easily see what the real and imaginary parts of a are. So because I won't assume any prior knowledge of complex analysis, the way that you do this if you have I in the denominator is by multiplying the top and the bottom of the equation by the complex conjugate. So the complex conjugate is just the same number, but you flip the sign on the imaginary part. So if you wanted the complex conjugate of this guy, well, that's going to be a negative 7 minus 6i. You just flip the sign on the imaginary part. Okay, let's do the same thing for down here. So we're actually going to be multiplying by 1. So nothing we're doing here is illegal, right? Now we can go ahead and multiply this out in the top and the bottom. Okay, so we have a negative 7 times 8. That's going to be a negative 56. Now we have a 8 times negative 6i, so that's going to be a minus 48i, right? Now what's going on with the bottom here? We have a negative 7 times a negative 7. It's going to be a 49. Then we have a negative 7 minus 6i, but then that's immediately followed by a plus 6i times negative 7. So in reality, those two terms are going to cancel, and we'll just be left with the product of these two guys. So 6i times negative 6i, well, the i's multiply and turn into a negative sign. And so then we have a negative 1 times negative 1 times 6 times 6. And what's that? That's just going to be 36. Okay, so then we have a negative 56 minus 48i over 49 plus 36, which is just the same thing as 85. This is our nice and final a. And so what do we say about the z particular solution? Well, that it was equal to ae to the 3ix, or we now know that that's actually the same thing as negative 56 minus 48i over 85 times e to the 3ix. And what do we want from this equation? We want the imaginary part. So in order to do that, we're going to need to multiply this, a minus 56 minus 48i over 85 by cosine of 3x plus I sine of 3x. And so we just used Euler's relation to break this exponential into a nice cosine and sine that are in the form a plus bi. Okay, so let's go ahead and do this FOIL. Well, we have a, first of all, negative 56 over 85 times a cosine of 3x. Then we have a negative 56 over 85 times a I sine of 3x. Nothing new there. Now we have a negative 48i over 85 times cosine of 3x. And then finally, we have a negative 48i over 85 times a I sine of 3x. So those i's are going to become a negative 1, and then that's going to cancel with the pre-existing negative 1. We're going to be left with a 48 over 85 times sine of 3x. And so this is our final particular solution for z, and we want y out of it. And we said that that was the imaginary part of z. So then what's the particular solution of y? Well, we take everything in this above equation that's being multiplied by an I. So in this case, it's these middle two terms right here. So it's a negative 56 over 85 times sine of 3x. then we have a minus 48 over 85 times cosine of 3x. So just like that, that is our nice and final particular solution for y. And if we were to do this by guessing a sine and cosine, this algebra would have taken a very long time. Okay, so we can then just go ahead and write our final solution, right? It's just the sum of the homogeneous part plus the particular part, which is what we just found. So what do we say the homogeneous part was? We have a e to the negative x times c1 cosine of x plus c2 sine of x, right? And then we add our particular solution, but in this case, we have a negative 56 over 85 times sine of 3x. Then we have a minus 48 over 85, and that's going to be multiplied by a cosine of 3x. And that's our final solution for y. And we never touched a cosine of whatever plus b sine of whatever. We only dealt with exponentials, which made our life actually quite a bit easier. Okay, well, let me know if you enjoyed this one, and if you want more, like, I guess, random tricks like this that can help you do things in a more efficient manner. So, thank you.